Good morning, everybody. It is a real pleasure to be here at Carnegie Mellon University and to be part once more of this Scott Institute Energy Week with all of you. The Scott Institute has built a reputation to bringing together engineering, policy, economics, and innovation to tackle the hardest energy challenges and humanity challenge of our time. That makes this forum here very special and very meaningful because the topic we're discussing today is not about academics, it's not about research, it's a systemic problem, and the energy dilemma, it is a wicked problem. And I think we have all the people that we need in the room to answer to that question. Carnegie Mellon sits in the intersection of energy, engineering, artificial intelligence, business. How cool it is to go to the Tepper Business School and the first thing you see is a robotic and a fat lab in a business school? How cool is going to the Scott Institute and see engineers working in power, very hard problems, hand by hand with policymakers? That is why this week is so special, and that's why I'm super honored to be here. When we talk about electrification, about artificial intelligence, about reshoring manufacturing, Costa gave us a good problem statement for what we need to solve today. All those are ambitions, but there is an essential question. Can the grid support what we are asking for it? Can we deploy enough electrons to the grid on time for the needs that we are seeing? If we want an electrified future, we must reinvent the grid that supports it. So, Costa mentioned it a bit. This is not the first time that Westinghouse, just one thing, just trying to change the slide, there. Westinghouse is not the first time that we have been part of the grid reinvention. In fact, the history begins here in Pittsburgh. In the late 1800s, George Westinghouse, with a lot of engineers, have built the alternative current system that made universal power distribution possible, not only in Pittsburgh, everywhere in the world. The innovation fundamentally reshaped society, industry, economic growth, and enables the third wave of electrification and well-being in our societies. Today, in 2026, we are celebrating the 140 years legacy of Westinghouse being here in Pittsburgh. You see this slide and you see that how things has evolved in those 140 years. But Westinghouse remains headquartered here in Pittsburgh, but now as a global company that is focused in nuclear energy. Our technology generates nearly half of the world's nuclear power. When you go to a power plant, wherever you go in the world, you're going to see an engineer from Westinghouse that is working on it. How to deliver this infrastructure, it is the challenge of our time. So the vision of Westinghouse is how to deliver reliable, affordable, low-carbon energy and scale and speed and secure the futures of the demands of the grid. Today, I want to talk about nuclear energy, deployed at multiple scales and enabled by innovation, because we believe that it's essential, alongside all the other technologies, to reinvent the grid of an electrified future. The grid today is under unprecedented pressure. Electrification accelerates through transportation, industry, building, artificial intelligence, those data centers that goes from megas to gigawatts are driving an exponential growth and requiring massive and continuous high-quality power. Renewables, energy storage, sensors, energy efficiency, all that is critical part of the solution, but some of those solutions don't work all the time, and that way the grid sometimes increase lack of firm, stable base load, and that is what Westinghouse and the nuclear industry is contributing into the problem. So why nuclear is back, let's say it this way, at the center of the global energy conversation. Not as a future aspiration, not as a technology from the past, it is really necessary for a grid stability, energy security, and decarbonization. If some of you are wondering where my weird accent is coming from, I was born and raised in Spain. I'm sure a lot of you, because you are all very nerds in energy, you have analyzed in all the details the blackout that happened in Spain last year. What was the base problem? Not enough base load, not enough density in the grid with a high level of renewables. So that is a good alert for us to see that we need to think about this problem in a systemic way instead of a technology way. When we think about reinventing the grid, it is important to recognize, as Costa told us, that it cannot happen without innovation. And when I was preparing this keynote, I was thinking, I would like for us to think about grid innovation through 3 archetypes. Now, new, next. Now it's about the grid's needs immediately. It's about keeping the lights on. It's about maintaining the reliability to avoid blackouts. It's delivering, for us in nuclear, firm, low carbon power with technologies that already exist. This includes the operating fleets, existing current plants, that actually we can obtain much more power from them with the right technologies applicable. But it's also about developing new reactors like the AP1000 that is fully licensed, proven, is operating. Guys, capacity factor of an AP1000 right now, we have 2 in the United States, 95%. If that is not part of the solution, I mean, redo the math and the modeling. It's not the only solution, but it needs to be included. There are not future concepts on this now, and that is the fastest way actually to solve the now problem. The new archetype, the new is about scaling what is ready to deploy. Where in nuclear, as sure you have seen a lot of hype about small modular reactors, micro reactors, but we also have long duration storage that is critical, and I think is the new thing that is gonna come to reinforce the reliability of our grids. New innovations allow us to adapt the grid and to changing needs without waiting decades. And the last archetype is next. Next includes advanced fuels, how I can produce more with less capacity, new manufacturing paradigms, robotics, digital twins, all that integrated in a system. We're starting to see things like BPPs, virtual power plants, how that integrates with light water reactors, no light water reactors. We're seeing fusion that is coming also on that solution. These are the innovations that are shaping the grid in the 10, 20, 30 years to come. And they might not be ready today, but if we don't start working on those problems now, we'll not have a solution to a problem that is already weak in the now archetype. Reinventing the grids required to think about this now, new, next, but not in a chronos way on timing. I would like for us to think more about the Plato and Aristotle concept of kairos, of it is the right moment to do what whenever is ready. Is that decisive instant when the decisions on the technology, the business, the society needs to happen at the same time, and of course on the policy side. That's why around the world, countries are planning significant expansions of nuclear capacity. By 2040, nearly 70 new reactors are expecting to come online, with major growth in North America and Asia. That aligns with the global goal to triple nuclear capacity by mid-century. And Westinghouse, obviously, we're very well positioned there because we have large reactors, small modular reactors, micro reactors, and we are also working in launch storage systems. For mature grids scale matters, and large gigawatts reactors remain in that now archetype, the backbone of reliability electricity systems alongside renewables, storage, and energy efficiency. So, in Westinghouse, because they asked me to present you a bit on our technologies, the AP1000 reactor is licensed, is operating, is ready to be built. We learned the lessons. When you are building a very large infrastructure, it can be a bridge or it can be a reactor. The learning curves are huge. We learned the scars. It was difficult, but we built already up on those, and we realized that, for instance, construction needs to be modular, that we need to fully digitalize the design so we can utilize AI to be sure that we can deliver in cost certainty and schedule certainty, because the grid needs are there. An AP1000 can power around 750,000 homes to the dome that you have presented, orders of magnitude of what we are talking here. And they are designed to operate over 80 years. That makes them very effective on the cost. For all the nerds working on costing modeling or energy modeling, I'm one of those. You see that when you have a capacity factor that is 95%, and you have 80 years of operations, your LCOE dramatically is incredibly competitive with fossil fuels. Of course, the capex to present it is a bit larger, but the benefits through the time, it is in a community, especially with renewables that they have a lower time, is really a perfect combination. But not every grid requires gigawatts. That is the reality. We are reinventing the grid. They are grids that they need more flexibility, that they are coming to a scale, that they need more flexibility into it, and they cannot absorb gigawatts in how they are being designed. That's why small modular reactors that basically they go from 100 megas up to 300, 400 megas came into play to secure the grid. What you are seeing on the picture is the AP300. It is what Westinghouse is developing, but you have to see this. It's very unique compared to other SMRs. Why? Because in Westinghouse, we thought about one single platform that is the same technology that has two different products. An AP1000 when the grid is mature, when megawatts are required, and an AP300, exactly same technology, so we benefit from all the lessons learned, so we can secure those grids that they need this capacity. With an expanded lifetime exceeding years, the SMRs can stabilize the renewable heavy grids over the long term. It can stabilize remote facilities in manufacturing that require these kind of facilities. But at the end of the day, you have to think something about building and de-risking. Having a strong understanding of construction material quantities, and now you are thinking how he's putting us here in a philosophical talking about Platon, and now we talk about construction material quantities. Well, at the end of the day, how big your footprint is on Earth when you are producing, it has a big impact on the cost. And why the cost is so important, because if I'm not able to bring the financial community behind these projects, then we don't have the impacts that we were talking before. So the AP300 is a safety-related footprint that approximately of 5 square meters per megawatt produced. That is very small. And that reduces the risk on construction, operations, and maintenance. We are talking about 0.4 acres required for safety-related buildings. So that said, any SMR carries the risk of a first of the kind because we have not built them yet on the United States. But on that TRL grid that Costa showed us, I think this is the next thing after the AP1000s in nuclear that we're going to start seeing being built. Even if I move on the grid and I go even smaller, even at a localized level, at a community level, remote capabilities, what you are seeing here is our microreactor. It's called Ibinchi. This, you have to forget everything you know about nuclear. It works more like a nuclear battery. So what it means that we don't have a coolant. We utilize heat pipes. It operates autonomously. It's been designed to operate autonomously for 8 years with no operations. We make it ideal to integrate it in a microgrid, in critical installations like hospitals, industrial activities, but also campuses, as Carnoli mentioned. Imagine the beauty with the history that we've been seeing in Pittsburgh about this, to have the power of the campus by a microreactor. So that is what we are doing, and this energy It is more infrastructure than actually logistics. And we are seeing that the grid is getting the heart of the electricity industry more than the power itself. And that's why we believe that microreactor is very critical. Of course, no single technology fits the needs that we have on the grid, as I was mentioning. So, surprise, we're also developing a technology that is not nuclear, is long-term storage of electrical energy for the grid. Why LDS? Because actually LDS, when it's supercritical, the technology bricks are very similar in how a nuclear reactor works. So for us, it's very easy to develop this technology and be sure that we are supporting the sustainability of the grid. So Westinghouse LDS technologies are designed for multi-decade lifetimes and can complement renewals, nuclear generation in the communities at a regional scale. And we have multiple projects that we are exploring. And usually those kind of projects, the same with microbenches, they happen at the community level. Very different from the large reactors that we work at the government, private-public partnerships. And last but not least, I would like to another important thing is about the reinvention on the grid and how we can bring more. The Department of Energy announced last Friday during a big conference that happened in Washington, D.C. last week, a program that is called Upscale. What is Upscale? Well, the nuclear folks, we know that actually with modifications on the current existing fleet, we can produce much more megawatts with the same structure that is already being built. The Department of Energy has realized this and incentivized all the companies to participate in this program. You can build like 300 up to 500 megawatts, depending on the nuclear capacity. This is an SMR that you don't need to build, that you already have. We need to work, obviously it's not simple, we need to work with the power conversion colleagues, the thermic experts, to be sure that we have that capability. But it's something that is coming. So maintaining the current fleet, it is really very, very critical for us. A point once more on the AP1000, as I mentioned before, 10 AP1000s can power 7.4 million homes. And today it represents basically 100% of gigas. As you know, President Trump was here in Carnegie Mellon almost a year ago, I mean in a couple of months, and he announced how we can contribute, how nuclear can contribute to the energy abundance. And we announced, or CEO Dan Summer announced a Pact-10 to deliver those reactors in the United States. So we're working very hard. Those programs are not easy. It takes time to contracting, to build the supply chain, to align the utilities, but it's moving forward and we hope we can make more announcements soon. All this is not feasible without innovation. So there are a lot of technology bricks that are very critical. And in Westinghouse, AI has already embedded across our nuclear life cycle. It reduced materials research for more of 50%. It improves the engineering productivity, the licensing of a reactor or an improvement for a power upgrade, reduce that timeline because we have all these new tools, and also the rigs, the construction schedule. AI enables digital twins and predictive monitoring. That's why I believe nuclear, with the rest of you in the room, we're going to work in topics like BPPs, integrated systems and integrated grids, because we have now the tools that is going to make that much easier to do it. Innovation also extends to many other areas, like fuels. Why fuels is so critical? Here in the pictures, you see the first deployment of LAU plus fuel in the United States. That means the level of enrichment that you put on the fuel. It means that when you ship that and you do innovation on that piece with the same capability, you can produce more, or you can reduce the operating so the cost is going to be better on the reactor. We are doing things like pretty amazing, like in this picture. This is a 3D printing or a button nozzle in nuclear. What it means that now, to accelerate the need of our customers, we are reinventing and introducing a lot of new technologies that they are coming from outside nuclear, but we are able to introduce them into our systems and projects. The last point I told you, remember the last archetype of innovation? Now new next. Westinghouse is also, we don't communicate broadly about it, but we are very engaged with the next generation of advanced fission, and we're also very engaged with fusion. What you are seeing here is ITER. Is landing a very important groundwork for fusion, and we contribute as well into that piece that we believe at one point in time, when that happens, we will be ready to support those fusion projects. Until then, fission delivers that scale, certainty, and reliability that we need. Just my final remarks. Reinventing the grid, it is not about choosing one technology over another. It is about advancing a systemic approach with now solutions to deliver reliability today, scaling new technologies, new business models, new policies, and investing in the next innovations that will define the increasingly blended and systemic system of a grid. At Westinghouse, we believe that nuclear energy, enabled by innovation alongside many other technologies and deployed across all these three archetypes, will unlock the future of energy. Thank you all for listening. We have a Q&A.
Yep. Okay. Thank you for that wonderful opening keynote for today. Really sets the stage for what we're going to hear later. We have a few minutes for questions from the audience, and as per tradition, if there are any students in the room and you have a question, you get priority. So now's your chance.
Okay, so I'm not a student, but students didn't speak up first. So fabulous talk, thank you. Could you talk a little bit about Westinghouse, what you're doing to think about recycling of the uranium as you're building these reactors that will come across the United States so that we can start to think about a sustainable cycle as well?
So that is a question that comes often not only related to Westinghouse. I mean, one of the things that maybe people that they are less versed in nuclear and they don't know is that it is incredibly regulated. So the US NRC regulates all that. For instance, if we don't have a solution of the end cycle, we cannot actually get a license to operate it. So in Westinghouse, we're very active at the governmental level, following and supporting all those policies, being sure that we are fully compliant. On the security of the supply of uranium, there are many ways. I didn't mention it, but Westinghouse is actually owned by Brookfield Renewables Asset Management and Cameco. Cameco is one of the premier leaders on uranium mining in Canada and help us actually to secure that supply chain. Also, we work with our ultra-Atlantic colleagues that they have developed a lot of technologies on recycling. So those are the actions that we follow very closely, project by project. Once more, it is by regulation that we need to do it. Also, something I would like to mention, on the end cycle, when we are calculating an LCO in nuclear, is very different from other energy sources. We need to include the cost of the dismantling of the plant. And if we don't have a plan for that, we cannot obtain an operating license. And thank you for the question, because usually we don't comment much about it, but actually it is for us in our industry a non-issue, but I think we have not communicated well correctly how it happens every day when people is working on those. So we include all that from the early stages on the R&D to be sure that we are compliant, and when we can improve, we are also proactive, working with different NGOs to propose new amendments to be sure that we'll have the supply and we will have also a good solution at the end of the cycle.
Zach.
Hi, I'm Marie. I work at startups in energy and materials, but my question for you is, what do you think today the biggest challenge nuclear faces to be a more substantial part of our grid. It's gone through a lot of reputational issues, but it seems to have dealt with some of those. So I'm curious what you think the challenge is today.
So for me, the challenge, and if you see, I have talked about those three archetypes, now, new, next. If I talk about the now, in how we can start building, and the AP1000 is an example. It is ready to be built. I mean, technically, we don't have issues. It's licensed. We know how to do it. We know how to build it. What are the challenges? The challenges is that the ecosystem of the energy systems have changed a lot. In the previous era of electrification, we used to have an energy provider, nuclear, non-nuclear. It works with a utility. The utility goes to the bank, get a loan, choose a constructor, there, bam. All the risk goes to the utility and to the vendor that is doing that. Right now, we are seeing an ecosystem that is very different because we are seeing the financial community coming with new innovations on how that risk can be shared. We have hyperscalers and manufacturing companies coming into the grid, say, how I can be part of that so we can build more. So the challenges right now is that we have all the pieces of the puzzle, and it's how we put all those pieces together. The policy side has advanced tremendously, and we see that piece has not been blocking, but it's putting all the pieces together in a new business model. We have now like 7 actors that you need to align to build one of these power plants. That is, for me, what is more challenging right now. We're getting very close because now we have identified all the pieces of the puzzle. We know each one of those stakeholders, what they want and how they want it. We have programs from the government supporting it. So basically, it's going to be a private-public partnership that is going to make it possible. But there is still the complexity of the contracting, legal, distribution or risk that we are still working on through all those stakeholders.
All right, I think we have time for one more question.
Thank you. It was a very interesting overview. I'm curious, and I hear in the news about the challenges that you're going to face in terms of supply chain, that like the companies that supplied you 20 years ago moved on to other things, like, and you need high precision in a lot of what you're doing. What's your plan for rebuilding a supply chain, and to what extent do you think there's going to be a cluster of activity in Western Pennsylvania versus where you're building the plants?
Yeah, so it's a very good question. And it's something that's why we believe that we are ready to build, because we have the supply chain that is ready to build because of the, I'm talking now specifically United States, because I understand that is the perimeter of the question. The 2 Vogtle plants that we built has helped us to understand that supply chain, what it is, what we need to reinforce. If you want to know more, actually next week in Washington, D.C., we are gathering all the supply chain. It's hundreds of suppliers that goes from very big ones to smaller ones in Washington, D.C., so we can discuss in all those areas. Basically, the philosophy at Westinghouse is buy where you build. So there are going to be, of course, big benefits from the Pittsburgh and Pennsylvania area, because traditionally we are positioned as here and a lot of our partners and suppliers are here. But locally, where those reactors are going to be built, they are going to benefit a lot for that local supply chain. Our critical point, and what we are working on very closely, those AP1000s, they have 137, if I'm not wrong, don't quote me on this one, but it is around the number of models that it goes. So you see, we also need to work with the shipyards, that basically are very, very large models that they are building in those shipyards in the United States, and then ship it and assembly. So we work in that ecosystem, but that is what I will say Westinghouse excelled, is building the supply chain with us because of that philosophy, basically buying where you build. You're welcome.
Thank you very much for all the great questions. And Lou, it's an honor to have you here this morning. Thank you very much. Please join me in giving her a round of applause.